so extending beyond the Cauchy horizon is something that requires a choice, and this choice is never explicitly explained. So there's some mystery there that we'll uncover. Then in part 3, we're going to look at the causal, topological, and geodesic structure of Kerr. So in particular, there's something remarkable happening in the Kerr exterior. The Kerr exterior has to be one of the most pathological examples of a space-time around, because in fact, every point in the interior, as soon as you pass the Cauchy horizon, right, of the interior, so that's after you've passed the event horizon, let's say. So the event horizon, you pass it, and then you get to the Cauchy horizon. So the event horizon is this surface, then you have this Cauchy horizon. As soon as you go past the Cauchy horizon, then in fact, there's a closed time-like curve that you can construct by threading through the ring singularity of Kerr. So that's what's called a vicious space-time, and it's about as bad as you can get. And the geodesic structure in the interior of Kerr is absolutely remarkable. We'll find that the kind of singularities that you have in Schwarzschild are nothing like the ones that we get in Kerr. In particular, in Schwarzschild, you might think that if you go into the black hole, you'll get crushed, and in fact, you're correct. In Kerr, nothing like that is going to happen. In Kerr, unless you're traveling perfectly in the equatorial direction, you're going to be totally non-singular, and you'll be able to pass through no worries at all. So that's remarkable as well. And then in the 4th part, we'll culminate in our Everest. So let me draw a mountain. This will be our Everest with some snow at the top. And here we will look at some major open problems, right? But in order to motivate and understand these major open problems, we need to do part 1, 2, and 3. But these major open problems, they will be beautiful. They're completely open. And I don't know any mathematician working on this. I myself have started to work on these. Okay. So I'm now going to make some remarks. I'm not going to write much down because I want to go faster through this, but just some preliminary remarks. So first of all, Kerr is discovered in 1963. There's a beautiful story as to how it was discovered and why Roy Kerr came to the solution he came to. It models the exterior of a rotating black hole in the context of astrophysics, but that's not a rotating star, right? So the multiple moments in Kerr are very precisely related to one another. We don't expect that of a rotating star, the multiple moments of a rotating star, to have the same features. So it's a rotating black hole more so than a rotating star, the exterior at least. The global causal and geodesic structure was understood really in the late 60s, but there's been contributions up to the mid-90s, and possibly the two most kind of sophisticated treatments of Kerr are by Chandrasekhar and Barrett O'Neill. So that came in the 90s. And as you know, there are various generalizations of Kerr. So Einstein-Maxwell, that's Kerr-Newman. Then you can add a cosmological constant that changes things somewhat. You can think about higher dimensions, in which case Kerr is no longer the unique solution. So those are the preliminary remarks. At the same time, Kerr is at the center of some of the most fundamental open problems in GR. So just to name a few: stability of the exterior, of course, that's something you've heard many times. Uniqueness and rigidity questions of Kerr, that's also something you've heard lots about. Stability of the interior, that means, is the interior of Kerr actually a faithful representative of the interior of black holes as we expect it to be? In particular, do Cauchy horizons persist? And in particular, all of this is really just a statement of strong cosmic censorship, right? So that's where that comes in. And then, of course, insofar as the exterior is concerned, astrophysics is concerned, does gravitational collapse generically lead to something that looks like Kerr? Namely, are astronomers and astrophysicists, when they template realistic black holes with the Kerr parameters and solutions, are they doing something that's legitimate? Now, as I said, the highlight of the seminar will be to uncover and elucidate and elaborate on major open problems that surround Kerr. And I've already given you some feeling as to which parts will do what. Okay, so how are we doing for time? 10 minutes in. Good. I have lots of notes. Okay. So let's start by going back in time somewhat.
Inside the cushion.
Not yet. Not yet, Peter. We'll just go back in history. I wish. Just wait till part 2. Okay. So the original form of the metric by Kerr is in these coordinates. So r, u, theta, phi. So these coordinates are the usual ones that you know, the spherical polars, but then u is like a t plus r type coordinate. And then in that case, the Kerr metric looks like this. And I'm showing you this because I'm showing you what happens. Why do we represent it in a different way and what that gives us? In particular, how do we actually understand the properties of Kerr? What do coordinates mean? How do we extend these and so on and so forth? So rho will always mean rho squared will always mean, okay, and that will give us our ring singularity later on. So notice that there are lots of off-diagonal terms. So, you know, a metric, you can think of it as a matrix, etc. But in this form, in these coordinates, there's lots of terms off-diagonal, right? And that makes computations difficult. However, what is nice about this metric is that what you notice is that the only singular parts, if you will, occur at r equals 0 and cosine theta equals 0, i.e. theta equals pi over 2. And what's happening here is that this particular form of the metric is the one in which it's easy to identify and pick out where it's going singular. That's the advantage of this metric. It turns out that this locus isn't just a coordinate singularity, it's a genuine, honest singularity, which is something we'll get onto in just a second. In a different coordinate system, there are more coordinate singularities that crop up. So you might think, okay, well, this is a great coordinate system. It is, however, there's lots of off-diagonal terms, which makes the computations in general more complicated. So that's why, by the way, we go to a different coordinate system. By the way, the Crachman scalar, so what I just said, namely that it's not just a coordinate singularity, it's an honest singularity. The Crachman scalar looks something like this. Then there's a bunch of terms here that I'm not going to write down. If I write everything down, we'll never finish. But notice this term, right? This is the crucial term. When this is 0, the Crachman scalar is blowing up. And when is the 0? Well, they're both positive, so this has to be 0, right? And the cosine has to be 0. Hence the pi over 2 and r equals 0. So this describes a ring. It's not obvious that it describes a ring because, of course, if you look at spherical polars, r is 0 seems to be here. But that's where you'll see that our intuition is failing us here because we can't think of these as Cartesian in any sense. So the Boy of Lindquist transformation was found by, as you can imagine, the authors Boy and Lindquist, and the idea is to transform. So you write u equals t plus r, and then you transform the t coordinates into TBL, and the angle into BL, and then here you have some integral which is an m dependent thing. I'm not going to write it out, but anyway, it's an m dependent. When you do this change of coordinates, the metric changes, and then what happens is that it becomes less non-diagonal, namely the diagonal terms dominate the metric, and you only just get a single off-diagonal term, which makes computations easier. However, the bad thing about this metric is that it's apparently singular in lots of in lots more places than the previous metric of Kerr. So you might think, okay, well, now comes the challenge of having to do away with these coordinate singularities, which a priori you don't know if they're coordinate singularities. Okay, so look at these terms, you'll notice, right, when sine is 0, you have a problem because the metric stops being non-degenerate. In particular, this component becomes 0. And so if you're contracting with vectors in this direction, you're going to get 0 all the time, despite the vectors themselves being non-zero. Non-degenerate, remember, means that it's what you require for the definition of a metric, is that if this is 0 for all W non-zero, then V must be 0. Right? So in other words, you're not getting 0, or you can only get 0 faithfully, so to speak. Whereas that doesn't happen if the sine component disappears, then that, any contraction with these components, well, purely these components will be 0, and so even though you're contracting vectors which aren't 0. So it's degenerate in that sense, and you have to do away with these degeneracies. But the asymptotics in this form are slightly nicer than in the Kerr original ones. And this is how you recognize that it's a spinning body. So let me just write it out. The asymptotics looks like this. Right, you've got some cube dependence. And so of diagonal terms. And then what goes here is dr squared plus r squared d theta sine squared phi squared. So that goes here. So you see from this immediately that the mass is m and the angular momentum J is ma. Okay, because you can then evaluate the usual ADM or the Komar angular momentum, etc., the formulae, and you end up getting that these are the quantities you get. So that form of the metric is useful in that sense. It tells you what's going on. It's a rotating body. This is, by the way, what I'm about to show you is where we're going to start seeing some magic. So take the m equals 0 limit. Right, this will give you, I hope for those who haven't seen this, that this is going to give you the first intuition as to what these coordinates really mean. So, I mean, at least it did for me. So what have I just done there? I'm taking the m goes to 0 limit, right, of the metric in the Boy of Lindquist coordinates. Now, what happens? What does this metric look like? Can anybody recognize what this metric is? Of course, I'm tricking you here. This is a flat metric. This is actually flat space, but in a weird coordinate system. What kind of coordinate system? Oblate. So it's called spheroidal oblate coordinates. So if Minkowski, if we're taking R3, say, right, then what these coordinates do is they, rather than a constant r, if you will, being a sphere, here a constant r will look more like an ellipse, right? So let me try and draw an ellipse. So the point is that these coordinates, even though this metric is representing flat space, these coordinates are geared to some kind of axial symmetry, right? And so in a way, it's not surprising that these coordinates are good for Kerr, at least for the exterior, because they're already based on the presence of an axial symmetry. Spherical coordinates have too much symmetry, in particular, a symmetry that doesn't exist in Kerr. So what's going on here is that we're using the right, allow me the analogy, with the right thermometer to measure the solution. We're using something that already captures this axial notion, right? The larger the A, the fatter the ellipse. Okay.
So Martin, one quick question
Yeah.
here. You said that Boy of Lindquist has some bad properties.
Yeah.
You said it's degenerate, which I did not fully understand.
Yeah.
But in this limit, is it still degenerate?
In
flat space limit.
In this limit, yeah, it is. There is some locus where it fails, yeah.
And where is that?
When you see this, when this guy is 0, when sine theta is 0, then if you contract vectors.
That's the focus around which your paraboloidal coordinates are expanded? Okay.
Yeah. So theta 0 is going to be the poles.
For the pole.
Right, because that's when sine theta. So if you look at sine, right, it looks like this.
Yeah.
This is sine. It's 0 here, and it's 0 here. So that's when theta equals 0 or theta equals pi.
All along the axis.
Yeah. So all along the axis, these coordinates fail. But
is that any more than saying that's true for any axisymmetric coordinates?
yeah, well, no. I mean, there are some axisymmetric coordinates that don't have this
Cylindrical
property.
coordinates.
Say again.
Cylindrical coordinates.
So you can write coordinate systems which don't fail, even in axial symmetry, but these ones do fail.
Okay.
In particular, if in spherical symmetry, this is something that's right. Spherical symmetry, they also fail here, by the way. But that's no problem, because if it's in spherical symmetry, I can rotate my coordinate system, right? Everything rotates this way. And then these poles were singular. They're no longer singular in the new coordinate system, so I can patch them, I can cover them. I cannot do this here. Notice I cannot do this here. If I change the axis of this thing, this ellipse will has a particular direction. It's not going to fit on the previous thing, whereas this sphere is going to stay its own thing. So fixing the coordinate singularities in this coordinate system takes more work, and that's why you could argue the Boy of Lindquist frame is a little harder to handle. But in a way, it's also more in keeping with the properties of the solution, namely its axial symmetry. Okay, so
So they fail on the axis. They can't be fixed with the little trick of a simple rotation because it's become oblate.
Yeah, it's become oblate. Yeah.
And but there is nonetheless something you can do. That's
yes.
where we are.
Yes.
Mhm.
So okay, so when you compute the determinant of the metric, right? When you compute the determinant of the metric, you get something that involves sine theta, and when you compute some other components, you get something like rho cosine theta. So when these are 0, so the Boy of Lindquists, right, are good when all these are non-zero. Okay. So if you want the Boy of Lindquist coordinates to cover everything that you want, you're going to have to extend them in some way and patch them in these regions. Now, it turns out that when this, you'll see that this being 0, this is going to correspond to the horizon. So this is actually interesting. Okay. This is going to correspond to the ring singularity, which is also interesting. So I put them in the interesting pile. The same goes for rho. So rho, of course, is, so I actually don't need this because rho incorporates the cosine. Right, remember rho squared was r squared plus a squared cos, remember this formulae. So when this is 0, it's interesting. When this is 0, it's interesting. But when this is 0, it's just, this is just a coordinate singularity. So this is just a coordinate, just coordinates. Okay. You can already see that the interesting failures of your coordinates, you can already track them where they're happening. Okay. So in particular, this function here determines will determine what kind of black hole it is. So remind you what this function is. It's r squared minus 2mr plus a squared. Okay. Now, if we go back to high school, okay, and we draw this as a quadratic, what do we get? We get something like this. So I'm drawing delta as a function of r. It's a quadratic, as you can see, right? It's a polynomial in r. There's some comment in the chat. Is delta the outer? Yeah, we're getting there, Richard. So this is what's called r minus. That's the Cauchy horizon. We'll eventually see it as the Cauchy horizon. R plus is the outer event horizon. So this is genuine event horizon. Okay, and then when A is large, when A is extremal, there's only a single root. Okay, so this is called extremal, and that happens when M equals A. This is called slowly rotating Kerr. Okay, so this is the physically interesting one. Well, at least we don't believe that extremal, and this is the fast Kerr. We don't believe that extremal black holes are out there. And then this is Schwarzschild. Which just has R equals 2M. Okay. So this function delta tells you what kind of black hole you are. Okay, that's how you figure it out. You look at delta and you look how it varies in terms of R. And now I'm going to show you a picture, which for me is a picture that I've taken a long time to understand, but I think it's the most beautiful picture of Kerr that's envisageable. By the way, so I've told you that the Boy of Lindquist metric fails at horizon, ring singularity, and axial poles, right? But that this is interesting and this is just boring. Okay, so this leads to a notion of block. So for slow Kerr, which remember is when M is bigger than A, for slow Kerr, we have 3 blocks or 3 regions. So R is bigger than R plus, that's the exterior. R minus is less than R, which is less than R plus, and then R is less than R minus. For extreme, which is when M is equal to A, there's only 2 regions. R is bigger than M, R is less than M. And for fast, it's all the same. So it's all one region. There's no event horizons, no nothing like that. So now comes the picture. Now comes in my mind, the single most important picture in Kerr. Okay, here we go. We're going to take a while to do this picture, but it's remarkable. Okay, so let's draw it like this. Okay. Good. Okay. My circle skills, I will try my best to do the best possible circles. Okay. Okay. So what do you think was so exceptional? We're going to go back a few slides. So these are the blocks, right? So decreasing R. This is the axial symmetry. This sphere right here, this locus right here, let me use a different color. This is R equals 0. So let me use a red line to denote singularity. Sorry for those who are colorblind. This is the equatorial plane, of course.
The Cauchy horizon, is it R equals 0 or at the edge?
No,
region three?
it's R minus. So it's the edge, exactly. It's the interface between region 2 and region 3. So let's shade it in. So this is the Cauchy horizon. If you understand this picture, you understand Kerr. And by the way, there's many more labels that are going to be put on this picture, so don't get too hopeful. Okay, and let's use a different color. Let's use blue for the event horizon. So can anybody tell me what was so spectacular? Oh, and how this is, by the way, very different from Schwarzschild. So this is the event horizon. R equals R plus. This is the Cauchy horizon.
Is there a simple relationship between A, this, the fraction of the speed of light,
A is the angular momentum.
the angular momentum, and the oblateness?
Yeah, I mean, the bigger the bigger the A, yeah.
But quantitatively, is there a simple?
So what exactly are you looking for?
The ratio of the major diameter to the.
Yeah,
to the
yeah,
vertical.
yeah. There are formulas. Yeah, yeah. You can express definitely. You can express some ratios of certain lengths and of interest in terms of A and M.
Mhm.
Yes. When you want to compute things like the local curvature of certain regions around, say, the event horizon, the local curvature is positive at the equators, but around the poles, it's negative somehow. And the actual formulae for the curvature there are troublesome and not analytic, and you have to expand them into terms of elliptic integrals and so on and so forth. But yeah, you can write some ratios for certain things, yes. Okay, so I'm not done with this picture. So you see, I'm gonna now draw this in a different color. Let's use the color green. So here, let's use a thick green. Okay, so you see how this line, this red line is R equals 0. So if we go back to the Boy of Lindquist, the expression for the Boy of Lindquist, right? This was the original form. But if we go back to the Boy of Lindquist form, what's remarkable here? Well, there are many things remarkable, but one of the things that's remarkable is that R can be negative. You see, in Schwarzschild, R can't be negative. When you have the maximal extended form of the Kruskal, when you have the Kruskal extension of Schwarzschild, R equals 0 is literally the end of the spacetime. You cannot get to R equals 0. Whereas in Kerr, there's nothing wrong with having R negative in this formula. R negative makes total sense in this formula. The metric preserves all the nice properties of being a metric. So what that means is that in this picture, right, you might think of this as an ordinary picture. It's not. The axes are exponential. So what that means is that beyond the sphere, beyond this sphere in an outwardly direction, R is growing. But as soon as I cross this sphere, okay, R goes negative past the sphere. As soon as R goes negative, you might say, how long does it take before it reaches the central, say, or the, you might say, let me use a small rubber for this. You might say that how long does it get before it reaches, say, here? It takes an infinite amount of R. So getting to the center, if you will, of this little sphere means the parameter R going to negative infinity. So the axes here are exponential. So wrap your head around that for a second. It takes a while to see.
So
Yeah.
a little confused. So what happens? How can I think about what happens when R goes to say minus epsilon? How do you?
Minus epsilon is easy. Minus epsilon is just here. Minus epsilon is the neighborhood of this sphere.
Okay.
As I go further and further in, my R is actually going to negative infinity. And at this central point here, R is literally negative infinity. So another way of seeing it is that when you travel past this throat, you could call it, right? When you travel past this R equals 0, what you're really doing is you're going from so let's say R is when you pass through this edge here, right? Take a sphere. So you're in this component when you're in the exterior region. Say you're an astronomer, you're a rocket or whatever, you have a rocket. So in this region, you're in region 1. Then you go into the black hole, you're in region 2. Then you go into interior, you're in region 3. When you get to region 3,
So is the throat the minimal throat radius R equals 0, or is R equals 0 in the plane of R?
no, R equals 0, you could take to be here. Yeah. Something remarkable is about to happen in just a minute. Hold that thought. When you pass through this, R starts to become negative. Okay. And then as the blue line goes out to infinity, then actually R goes to negative infinity, right? So this is,
What is the blue line down there? That's the.
it's just a locus of constant negative R.
Does the R equal 0 surface depend on A? The extent would the R equal 0 surface encompass more or less of the or less volume depending on A?
Are the properties of the geometry of the R equals 0 surface?
Does it depend on A, the angular momentum?
Yeah, I'll show you in a second what it does. It's actually magic. That's actually magical. We're about to get to that. But so basically in this diagram, the blue line is here, right? In this diagram, the blue line is here. Peter?
Yeah.
And as the blue line goes further and further in towards the center, what's happening is that this is actually going out to infinity. So the center here is, if you will, the sphere at infinity, but in this component.
Sorry, we're not. It's confusing. It's not inside the throat, we're outside the throat.
That's right, we've passed through the throat.
But topologically, aren't we? I mean, how do we get from inside to outside?
Well, topologically, it's easy. We just pass through a barrier. There's no inside or outside.
Going in.
We are going in, but the geometry, when we go into the black hole, there is no central point. You'd merely pass through a throat and into another universe. And the way the reason why this picture is beautiful is because it tells you, for the outside, it tells you what's going on, right? You're in the rocket ship, you go into the black hole. Okay. Then you're in region 2, you're in the interior. When you pass region 3, the Cauchy horizon, you're in the deep interior. Now you might think, okay, maybe the deep interior has singularities and so on. Yeah, it does, but actually it only has a ring, so you can pass through it very easily, unless you're traveling on a geodesic, which is exactly equatorial. Unless you're exactly equatorial, you'll pass through the singularity, no problem, right? And then moreover, as soon as you pass through the r equals 0, which is this throat here, then actually gravity, rather than being an attractive force, becomes a repulsive force in a way. And the mass becomes negative somehow. And actually, you pass through unharmed into this extension. So in this little sphere is actually an infinity, a spatial infinity, right? Which is represented here.
So does inside and outside not really have a meaning anymore?
Well, it does. It's with respect to a particular choice of surface. Right? Inside and outside are only meaningful if you identify for me a surface that you're talking about as being the outside of which or the inside.
A 2D way of thinking about this is therefore not useful. Right? I think of it like this big cube. I'm going in, then I come out at the bottom. I don't actually come out here, but that doesn't make a difference.
No, the two-dimensional way is useful in the sense that, this part of the picture is unproblematic, right? I'm just passing through the surfaces, the event horizon, the Cauchy horizon, etc. What's interesting is that unlike what happens in the interior of Schwarzschild is that it literally looks like this. Like if you're traveling.
I'm just having trouble with you patching onto the new one.
Well, what part are you having trouble with?
If you have this funnel.
Yeah.
And then you have, so this is the other universe.
Yeah.
One universe is this part.
Yeah.
And then you have this funnel.
Yeah.
Yeah. You go through here, so in the throat, you go all the way down.
Yeah.
You actually arrive here and not here.
That I don't see the issue there. Yeah.
Connects, right?
Yeah, that's right. You end up on top of the pit.
There's a difference between this surface and this surface, right? The way we've drawn it.
Well, you're talking about whether there's a side difference here. That from the point of view of the surface, there's no difference, because from the point of view of the surface, there's only two coordinates. It's whether it's lengthwise and heightwise. So whether you're on top or on the bottom is actually, that comes from your intuition in R3, embedding in R3, which you should drop here.
Okay.
Insofar as the surface is concerned, the only relevant thing is the coordinates on the actual plane, which don't care about the sidedness of the paper. So now here we go. What's even more remarkable? Let's start really getting some magics here. So what's completely crazy, right, is that, okay, let's analyze. Let's be a bit more careful. This is the ring singularity. Okay, this is a locus where r equals 0 and cosine theta equals 0, which means theta equals pi over 2. Okay, it's a ring because this surface is the whole surface r equals 0, but simultaneously you need cosine theta equals 0, and that means that this angle here must be 90 degrees, and that's why it's a ring. At this ring, the Crachman scalar blows up, like I showed you before. In particular, the denominator, there's a denominator in the Crachman scalar that looks just like this, right? So it blows up, if you will, to the power of rho squared. This is rho squared to the 6th, okay? So that's how it blows up. And that is really true, a curvature singularity. So you might ask, okay, what is the topology? What is the shape? What is the, what are the properties of, of this surface, right? So can anybody tell me what happens when they take an orange and they cut it through the middle? What do they produce? They produce two components. And what are the surfaces of those components? What are the peels? peels are hemispheres, right? This is a hemisphere. You produce two hemispheres. Yes? Now, a reasonable question to ask is, what is the geometry of those hemispheres? So those hemispheres, you know, topologically, they're just a disk, right? It's just a disk that's been squashed a little bit. Now, it turns out that because of the bending happening in the throat, right, and this ringy singularity just being in the middle like this is, by the way, where the two-dimensional intuition is going to fail you, because, of course, this picture, the ring seems to be blocking any passage through, but of course it's not quite like that, right? Because it's actually a sphere there. What turns out to be the case is that the actual geometry, right? You're in a black hole, right? This is extreme stuff. You're in a black hole. Actually, the geometry of this is flat. Right? You can compute this. So despite being as deep as you like into a black hole, despite being as close as you like to a singularity, the actual space, the spatial curvature, if you will, of these hemispheres which hug the singularity, they're flat.
This is precisely the R equal to 0 hemisphere you're talking about. And you're talking about the 2D curvature of this
Yes.
hemisphere, I see.
Yes.
So it looks like half of a sphere in the diagram, but you're saying that if you went and looked at the metric, it will actually be flat.
It'll like a cylinder.
It will act like a cylinder. And then as you approach the ring, what happens?
Well, as you approach the ring, somehow, this ring is the thing that, right, separates these two things. Somehow, as you approach the ring, the curvature blows up. And so what must be going on is that these flat disks are being infinitely curved, but only in one direction, only in the direction perpendicular to the disk.
Where you are trying to join.
Yeah.
Okay.
Well,
Flat in this two-dimensional surface, but there is a real kink.
There's
where
a
you're trying
kink.
to join
Yeah.
the two guys.
Yeah.
Okay.
is there an analog where you have, let's say, a cube, and then if you're talking about a Gaussian curvature, all of it would be contained at the edges or the points?
Yeah, so good. So Richard's point is that, say, if you have a cube like this, and say you zoom in on this part, so let's zoom in, right? Then you can kind of make it smooth by going like this, and then you introduce curvature. But as this line goes increasingly close to the corner, the curvature here blows up. It's a little like that. Yeah, you can think of it like that, kind of. So, you know, people say, you know, yeah, Kerr, you know, singular, etc. Actually, Kerr is very nice in a way. You know, it's basically flat in these disks. There's only one ring singularity, and moreover, the only incomplete geodesics are the ones happening exactly at this ring. So, in particular, if, you know, if I'm an observer, let's draw our magical picture again, which is I think the most important and beautiful picture to represent Kerr. If I'm any observer, right, remember this whole guy is rotating. There's an axis of symmetry, it's rotating like this. What this means is that unless I'm this particular geodesic, right, I could be time-like or null. We'll prove later on in the later lectures of the mini-series, we'll prove that in fact these have to be time-like or null. But what happens is that as soon as I have some angle, then I get thrown around, and maybe I go in, and maybe I go in again, but then eventually maybe I come out, or maybe I go through the throat, etc. We don't know. It's a very chaotic kind of motion. But the point is that you have to be very, very fine-tuned. You have to be exactly equatorial to actually be a singular geodesic. So, in other words, the fate of an observer falling into a black hole in Kerr is wonderful. Just move yourself from the equatorial plane a little bit, you'll be fine. Okay. I have just
Fine in the sense of fine from the ring singularity, but not fine from the Cauchy horizon.
well, the Cauchy horizon is just an invisible surface that does nothing here. The Cauchy horizon does nothing
I
here.
thought that's what you and you know, in your paper, you showed that there was exponential rise in curvature as opposed to Cauchy rise.
Well, that's different. That's because Ramesh is perturbing it. And he's seeing what happens when you throw stuff in like that's perturbing the actual geometry.
Also, mostly it was less strong.
Yeah, this is the exact kerr. If you have a test particle in exact kerr. Of course, in the real world, we don't expect, well, this is for the latest, lectures of the mini series, but the point is that the main mathematical open question in general relativity is, insofar as these things are concerned, is whether or not this picture remains valid when you perturb it. Yeah. Okay, so now I want to talk very quickly about the ergosphere, and then I'm going to stop just at least 5 minutes before, so we have time to collect our thoughts or whatever, and like prepare for the colloquium. So this is another wonderful picture where, let's draw the picture once more. Okay, so this is r equals 0. This is r equals r minus. This is r equals r plus. This is r equals 2m. And this is, say, r equals infinity, the sphere at infinity. So you can look at which component GTT equals 0. When does GTT equal 0? That's a time component. And what that tells you is that when you pass through this region, an observer, which even traveling as close as you like to the speed of light, is not going to be able to change or to maintain the angular coordinate. So in particular, past this point, so past r equals 2m, so r equals less than 2m, then the azimuthal angle, right, which is remember this angle, is monotonic in any trajectory. Any time-like observer that's hovering around the black hole is actually going to be co-rotating with the black hole as soon as they pass r equals 2m. And you can delineate where this surface lies, right? How does it depend on A, for instance? And it turns out to look like this. Now, I have to get this right, but it turns out to look like this. Kind of comes in and out like a butterfly. And here it changes. So it goes like, it's a butterfly, but it's been rotated. And then the blue picture, which is, let's use a thicker version. The blue picture, the blue shaded region, is this ergosphere. Now, of course, you're familiar, you've heard of the Penrose process, etc., where if you're in regions, right, if you're in regions 1 intersecting with this ergosphere, so namely this region now. So let's see, region 1 intersect, yeah, so this region. Then you can extract rotational energy from the black hole by throwing things into the black hole. But what's interesting is that that the actual local, sorry, the local curvature here and here is becoming negative. So this picture is not really faithful as a, embedding it in say R3. And exactly the opposite happens when you're passing through this this inner surface. So something is changing or other in the geometry that's making these surfaces change shape as you go through the throat somehow. I think that's a good place to stop. More to follow. Part 1 of part 4.
Is there a Penrose process for the guy in the other universe? Using the other wine glass. So,
Yes, there is. Yeah, there is.
Moving angular moment.
More complicated.
Okay.
It doesn't happen the same way. So when there's an asymmetry. The outside of the Kerr black hole does not behave like the other universe past the throat. And you can see that from the metric components. The metric components don't have that symmetry. In other words, r equals 0 is not a fixed point in the symmetry. You can't just reflect the black hole. This is where the throat picture is misleading us once more. This is not an exact picture. This looks symmetric around r equals 0. It would be in Schwarzschild. It is not in Kerr. In Kerr, once you go past the Cauchy horizon, and then once you go past r equals 0, somehow gravity ends up repelling you. It's easier to escape to infinity than it would be otherwise. And the ergo mechanics are inverted somehow, but there is still a process. Oh, Jacob has a hand. Yeah, Jacob.
Thanks. That was a wonderful presentation. I learned a lot. Thank you so much. Am I coming through okay?
Yeah, the sound's pretty bad, but you can go ahead.
Sound. All right. I've been having some trouble with my microphone. Is this better?
Yeah, it's slightly better.
Couple questions. One.
You have to be quick though, because the colloquium's starting soon.
Okay. Quick question. One, that magical picture that you drew, how does the magical picture look differently for Rienster Nordstrom?
I need to draw that for you. That'll take a while to answer your question. We'll do that next time.
Next time. Second question. How do the different parts of this picture map onto the parts of the conformal diagram for the maximally extended?
Forget the conformal diagram. Forget that, like, part of the things I'm going to try and make clear is that the conformal diagram, is insofar as the exterior and the interior region is concerned, is fine. So everything up to region 2,
yep,
including region 2. But the topology of the conformal diagram is completely misleading. Every point is an S2, whereas here, manifestly, that's not the case.
You see.
So the Penrose diagram for maximally extended, Kerr is really, it's a visual aid, but don't trust it.
Okay.
It breaks in region 3 and everything beyond region 3. It's no longer faithful. The topology changes. I'll even show to you what the homotopy type is of the fully extended thing. You'll realize that, wow, we're really a long way away from S2 cross R2, which is what is in Schwarzschild.
So there's a fundamental problem with representing the story using Penrose diagrams that you can't
Absolutely. Absolutely.
Okay. That's really interesting to know.
But it's good in the exterior, and it's good up to the Cauchy horizon.
Very misleading, though, in a lot of textbooks, then.
Completely.
Yeah.
Completely misleading.
Good. This is very good to know. Thank you.
Forget the textbooks. Bye-bye. Bye-bye, everyone.
So, Martin,
Rewrite all the books. Yep.
do you have a